Alright folks, so fluid electrolyte balance and fluid movement. This is 27-3 and 4. I believe this is, well it says on here, but it goes through 27-3 to 27-4. That's what I think we're covering in this mini lecture. Alright, so here are the two compartments. Your intracellular fluid compartment and your extracellular fluid compartment. In this particular image, we're not dividing the ECF into interstitial and plasma. We're just saying it's both of them, the interstitial and plasma. All right. Now, fluid moves between the two compartments readily. If the cell became dehydrated, fluid can move in here. Fluid is always moving from a hypotonic environment into a hypertonic environment. There is no such thing as active transport of water. Now, we can control the movement of water by either adding aquaporins to a cell membrane or taking them away. And you know ADH does that to the renal tubules anyway. It allows aquaporins to be added. But there's no such thing as an active transport molecule that pumps water. It just follows the higher solute concentration or the hypertonic environment. But this is showing you a balance. For example, the balance here is this. I just absorbed 2,200 milliliters of water. That's what I just absorbed, all right, across the digestive epithelium. And I have 300 milliliters of metabolic water I just added, so that's 2,500. So I have 25 milliliters of water I just added to my body. Now I better lose 2,500 milliliters of that water as well. So let's just make sure we do. I lost 1,200 in my urine, right here, 1,200 in my urine. 1150 in my insensible sweat and my breathing. Now this is insensible. Well, it actually could be. Yeah, it's insensible. I can see why it's insensible. Insensible. The reason why I know it's insensible sweat you don't notice because it happens every day. You don't notice it, is because this is telling you. This is when you. This is telling you this variable amount is like if you exercise, you lose this sweat from sweat glands. But this water vapor lost at the skin and the lungs is called insensible sweat. And you don't really notice it. It doesn't saturate your t-shirt, give you sweat rings or anything. It's just vapor that you lose every day. And then we have water loss in the feces. That's 150. And then, of course, we have variable, but we have no number for variable. All right. That's 0. 5 and 5 is 10. Carry the 1. 4, 5. 2,500. 2,500 equals 2,500. Now, obviously, if I sweat a lot from working out, I got to drink more. But these have to equal each other or this throws things off. Now, what the heck is metabolic water? Well, if you remember, at the end of the electron transport chain, oxygen receives electrons. And it receives 4 electrons and 4 protons. And it turns into water. All right. That's the terminal electron acceptor at the end of the electron transport chain or electron transport system in the mitochondria. That's called metabolic water. Some organisms use metabolic water exclusively and never have to drink, like the kangaroo rat out in the desert. So this metabolic water, and we do make metabolic water every day. We don't make much of it, but we make a little bit every day. So that's the balance in the fluid movement in our body. All right, what happens when we have an imbalance? We rebalance it. So, for example, here's an isotonic solution. Your cells are isotonic to your extracellular fluid. It's usually that way. All right, but we lose water from our extracellular fluid. It could be you're hemorrhaging. It could be you sweated a great deal. Whatever it is. All right. You lose water from my extracellular fluid. You didn't lose these solutes though. That makes this hypertonic. To what? To this, which is hypotonic. Why am I saying that? Because they used to be isotonic and this one lost water. It lost water only. So now if I lose water and don't lose the salt, then I'm hypertonic. So now water always travels from a hypotonic environment into a hypertonic environment, that arrow right there, until I reestablish isotonicity and osmotic equilibrium. But in doing so, I dehydrated my cells a little bit, did I not? Did I not take some water out of my cells and dehydrate them? I sure did. So this kind of movement happens all the time. And it happens back and forth. It goes both ways. If my cells lose water, they become hypertonic, the water moves this way. So I have this constant fluid movement to maintain osmotic equilibrium. And there's no active transport of water, but it goes from hypotonic environment into the hypertonic environment every time. In the water balance, this gives you some approximate water content of food. And when you're measuring input and output, intake and output in the hospital, you estimate this, how much water is in the feces. I mean, you have to look at the stool of the patient, but you estimate how much water is in it, and you can see that there's an estimate there. You physically measure the urine. They're usually catheterized, and their urine is being collected into a bag, and you can measure that output of urine in the bag. So you have these approximations, and you have some actual measurements, but the input and output must be measured. You're trying to keep them in balance. By the way, don't memorize these numbers. Please don't memorize them. All right. Electrolyte balance. Now we're going to talk about different mechanisms for electrolyte balance. I'm going to sound like a broken record because I'm going to be talking about some hormones you already know a lot about, like PTH and calcitonin. I'll be talking about those. All right. Like aldosterone. You're going to say, are you sick of talking about that, Kiggins? And no, maybe a little bit. But we'll talk about them again. We'll talk about water, which is ADH. And of course, if I retain water, it changes all of these. So electrolyte balances, we're going to talk about the hormones that control them. And by the way, potassium is aldosterone too. Remember that a high potassium leads to aldosterone secretion. Okay, so we'll talk about these right now. All right, so first of all, I don't want you to memorize all of these normal values. Please don't memorize the normal values. Do know these words. High sodium is called hypernatremia. Low sodium is called hyponatremia. High potassium is called hyperkalemia. Low potassium is called hypokalemia. High calcium is called hypercalcemia. Low calcium is called hypocalcemia. High magnesium is called hypermagnesemia. Low magnesium is called hypomagnesemia. High phosphates called hyperphosphatemia. Low phosphates called hypophosphatemia. High chlorides hyperchloremia. Low chlorides hypochloremia. All right, and usually chloride follows sodium. So usually when you're hyperchloremia, you're also hypernatremia. And but not always though. Not always. So I want you to know these words. I don't want you to memorize these numbers. I don't want you knowing all of the normal values for everything. It's something I'll give you if I want to ask you a question about it. I don't want you memorizing all the signs and symptoms of all of these. I do want you to know some of the causes. All right, just some of them. Oh, not actually. Yeah, just some of the causes. And by the way, in the signs and symptoms, I don't want you to memorize all of them, but a couple times I'm going to say, hey, makes your heart stop. And when I say something like that, you're going to have to say, wow, that makes my heart stop. So, all right, so let's talk about some of these. First of all, sodium's controlled by aldosterone. High sodium's hypernatremia, a low sodium's hyponatremia. And what this leads to is blood pressure problems because water follows sodium. So look at if I have this is actually counterintuitive. This is actually counterintuitive because what you're going to think here is this. You're going to think that if I have high sodium, water should follow it. I should have increased blood volume. That's what you're going to think. And it shouldn't be a circulatory collapse. It should be a high blood pressure problem. But the reason why that's counterintuitive is because the major cause of hypernatremia is dehydration. That's the major cause. All right. Typically speaking, you don't become hypernatremic by eating too much salt. And the reason being is because, yeah, your sodium goes up, but the water follows it and dilutes it out. So the way you become hypernatremic is by removing water and not removing salt. And this is a dehydration. So you do have reduced blood volume. You have reduced blood volume and eventually circulatory collapse. And that's a little bit of a paradox there. All right. So that's that. Now, the most common electrolyte imbalance is sodium, but the most deadly electrolyte balance is potassium. All right, just you do need to know that. Sodium is the most common electrolyte imbalance, but potassium is the most dangerous electrolyte imbalance. Why? Heart problems, muscular weakness, including the heart. Hyperkalemia and hypokalemia affect the heart. Both of them do. And otherwise, you got to keep it normal to keep your heart beating normal. All right, and acidosis affects these, and alkalosis affects these. You probably already realize why. Because if I change my proton concentration, it replaces potassium in the exchange of sodium in the kidneys. But I'll wait till I get to the pH to talk about that again. All right, calcium. The two main hormones here are calcitonin, which lowers blood calcium, and parathyroid hormone, which raises blood calcium. And any problems with these hormones can lead to either hypocalcemia or hypercalcemia. Look at hyperparathyroidism leads to hypercalcemia. That makes sense. Parathyroid hormone increases the blood calcium. These affect the heart. Cardiac arrhythmias. These affect the heart. Cardiac arrhythmias. Similar to potassium, calcium, high and low calcium affects the heart. High and low potassium affects the heart. The heart is a muscle. All right. It's also skeletal muscle weakness, but the heart is a muscle as well. All right. Magnesium, I'm not going to spend a lot of time on this. It actually is indirectly affected by calcium. All right. So you can see that, and by the way, magnesium affects calcium and calcium affects magnesium, just so you know. So it's linked to calcium. I'm not going to talk a lot about the magnesium. Phosphates also linked to calcium. And by the way, I'm saying these because it has to do with bone minerals. Magnesium's in the bone, phosphates in the bone. All right, that's why I'm saying that they're linked. So phosphate I'm not going to talk a lot about, but it's linked to the calcium. And then chloride usually follows sodium. That's what this usually does. Chloride follows sodium. So if you're hypernatremic, you're usually hyperchloremic. All right, so that's going on there. This is showing you a homeostatic circle here. If I have increased sodium concentration, my hypothalamus is going to detect that, and I'm going to release ADH. ADH tells my kidneys to reabsorb water. I dilute out the sodium, and I come back to normal. Okay, what if I have decreased sodium? Well, if I have decreased sodium right here, decreased sodium, my hypothalamus detects that. My ADH secretion decreases. All right, so I'm not retaining the water. I actually urinate more water. I urinate more. So I decrease my body water, and that well, it doesn't really dehydrate me, it's bring me back to normal. But I increase my sodium by removing that water, and I come back to normal. Oh, look at that. I said 4% a couple lectures ago. Remember how ADH is also called vasopressin? And I said the osmolality is the major stimulus. I think I said a 4% change in osmolality causes ADH to be secreted or suppressed. Now I'm talking about secreted or suppressed. Your book is saying 2%. I'll go with 2. I might have actually said 2 to 4 in my previous lecture. And by the way, that equals change. All right. And remember what I said, ADH is also affected by blood pressure, but the vasopressin is not secreted until there's a 10 to 12% change in blood pressure. I mean, it's very insensitive to blood pressure. There has to be a major change in blood pressure, whereas it's very sensitive to the osmolality. Okay. This is the collage showing you how we respond to sodium changes. All right, what are we doing here? We are doing extracellular fluid volume. Now, I have no transport mechanism for water. So what am I doing first? I'm gaining extracellular fluid volume. So I have a gain in extracellular fluid volume. I don't have any direct way to pump water out of there. All right. But here's what I have. If I have extracellular fluid volume, that's going to give me an increased plasma volume, and I can secrete atrial natriuretic peptides and brain natriuretic peptides. Remember, ANPs are released from the atria, and BNPs are released from the ventricles. What these do is these increase sodium loss in the urine because they shut down aldosterone. They shut down angiotensin 2. They shut down all these things. We already talked about it. They do the opposite of the renin angiotensin aldosterone system. They decrease thirst. Well, if I increase sodium in my urine, I increase water in my urine. Water follows salt. What else do these ANPs and BNPs do? They inhibit ADH and aldosterone and things like that, and epinephrine, which is a vasoconstrictor. So they vasodilate. All of this leads to decreased blood volume and decreased blood pressure, and it brings me back to normal. So see how ANP and BNP, the natriuretic peptides, act to control extracellular fluid volume. What happens if the volume goes the other way? Well, this is the renin angiotensin aldosterone story. I have decreased extracellular fluid volume that leads to decreased blood pressure. My kidneys detect that and secrete renin. Okay, I really don't want to do it again. All right, one last time. Angiotensinogen is converted to angiotensin 1 by renin. Angiotensin 1 is converted to angiotensin 2 by ACE. Angiotensin 2 does a whole bunch of things. It causes aldosterone to be secreted. It causes ADH to be secreted. It causes you to be thirsty. Okay, so what do these things do? By the way, it vasoconstricts. I missed one. All right, increases sympathetic tone. Does that. I mean, it does a whole ton of things. You know them all already. Aldosterone goes to the kidneys and it says, hey, increase sodium retention. Water follows. And so there, if water follows the sodium, which is being reabsorbed into your body, that decreases water loss. There's less water in your urine. Now you're making small amounts of concentrated urine. All right? Because you pulled out the sodium and therefore you're pulling out the water. Water follows sodium. So you have small amounts of urine. What does ADH do? ADH goes to the kidneys and puts in aquaporins in the distal convoluted tubule in the collecting ducts and says reabsorb more water. So that's what all of this does. And the bottom line is you increase volume and increase pressure and you're good to go. This is the collage of what happens when we have either increased extracellular fluid volume or decreased extracellular fluid volume. All right, now look at this. No, that's not something I want to talk about. Cardiac arrhythmias, effects on the heart. See, both low and high affect the heart. I do want to point that out. Heart. Low and high potassium affect the heart. Now, we are very good at reabsorbing sodium. We are horrible at reabsorbing potassium. Let me give you some numbers. Our gains or loss per day for both sodium and potassium are about 50 to 150 milliequivalents per day. Oh, I'll come back and explain an equivalent in a second. This is for both sodium and potassium, both of them. You're going to say, well, that doesn't mean that we are great at conserving sodium and poor at conserving potassium. Yeah, it does. Because normal sodium is about 140 millimoles per liter or milliequivalents per liter. And that's the same as millimole per liter. I'll explain that in a second. All right. Normal potassium is about 3.5 to 5 milliequivalents per liter. And by the way, the milliequivalents equals millimoles. If you go back and look it up, it equals it. So what I'm telling you is you could gain or lose in one day about a third to a whole amount of sodium. So you might need to gain a third of the sodium. Or you might need to gain all of the sodium that you have per liter in a day. But you see how 50 to 150 compared to 140. It's like a third up to the same amount. But potassium, what you gain or lose in a day, is 10 times to 30 times your normal value. I'm talking about 1/3 to 1 here. I'm talking about 10 times to 30 times here. We are horrible at conserving potassium. We have to gain 10 times to 30 times in a day what our normal value is. For sodium, we have to gain 1/3 to 1 what our normal value is. You see how we're really good at conserving sodium, or we're horrible at conserving potassium. And sodium is the most common electrolyte imbalance, electrolyte, but potassium is the most dangerous. All right, what the heck is this equivalent anyway? An equivalent equals a mole of electric charge. That's what it equals, a mole of electric charge. All right. So 1 mole of sodium equals 1 equivalent of sodium. Why? Because sodium has 1 charge. So a mole of sodium is a 1 mole of a charge. 1 mole of chloride equals 1 equivalent of chloride, because it has 1 charge. It happens to be negative, but I didn't say what kind of charge when I said an equivalent. I said a mole of electric charge, because it has 1 charge. Same with potassium. Potassium has 1 charge. A mole equals an equivalent. But we do have these cations and anions that have more than 1 charge. Calcium. Calcium has 2 charges. So half a mole of calcium is 1 equivalent. Because a half a mole is actually a mole of charges, because there's 2 charges per calcium. So I hope you see that. It's really, I'm going to sit here and say it's chemistry. It's biology too. This is also biology, obviously, because we're talking about equivalents. And by the way, a milliequivalence is just 1/1000th of an equivalence. That's all. That's all. It's not anything fancy. So when we say milliequivalent, if it has a single charge, either a +1 or a -1, it's the same as saying millimole. But if it's calcium or phosphate or something like that that has more than 1 charge, then you have to do a little bit of math to adjust it. That's all. That's what an equivalence is. Here are some other hormones that influence our water retention or water loss. Estrogens. This is a steroid like aldosterone. It increases sodium chloride reabsorption like aldosterone. So estrogen is a synergistic to aldosterone and increases water retention. If you're female, you realize this because you will have bloated periods during your menstrual cycle, and that's because you're retaining water when your estrogens spike. Progesterones do the opposite. They block aldosterone, and you lose sodium. You don't retain the sodium, you lose it. So progesterone does the opposite of aldosterone. It blocks it. All right? And if you're female, you probably realize that, because during your menstrual cycle, there's a period of time when your progesterone spikes and your estrogen drops, and you would lose the water. All right, glucocorticoids like cortisol, these act similar to aldosterone and increase sodium reabsorption. All right. By the way, there's a disease called Cushing's disease, which is high cortisol, and you get a moon face. You get a puffy face. You get an edematous face because cortisol leads to edema. All right. This is the parathyroid hormone. That excess parathyroid hormone will lead to high calcium. So high PTH leads to hypercalcemia. And that's because parathyroid hormone is involved in osteoclast activity and absorbing calcium from the intestines and things like that. All right. And that's it for this part, folks. Next part coming up.